what we've got, and right now it's a logarithm. Now, logarithms can become exponentials by using this formula. Y equals log base A of x. That converts, and it can go either way, that's why we draw the double arrows, that can convert into x equals AY. Now, when we go to convert these, we need to make sure we label the pieces. So right now it's a logarithm, so that base is the A, the 625 is the x, right? And that 4 is going to be the y. So what would that look like now as an exponential? So as an exponential, that's going to be 625 equals now 5 to the 4th power. And we know that's a true statement, right? Because 5 to the 4th power is what? Is 625.
So true will be the answer?
No, all I want on this one is this. This is the answer right here. I converted that logarithm into an exponential. And that's all I want you to do. Convert it from one to the other. Question 8. Question 8 is 100 log base 10 of 3. Now, there are a couple of different ways of working this one out. What I'm going to have you do is just use your calculator. You can also use the rules of exponents as well. But let's go ahead and just use our calculator. So the first thing we would do, order of operations, is we would do the power first. Now, what do we know about log base 10? When it has a log base 10, that means that we can use, the log key in our calculator. And I'll use this calculator because this is the most common type of calculator. Okay, so the first thing I'm going to do, clear that out, we're going to do the power. So log base 10, that means we can use the log key in my calculator. So I'm going to take log of 3, and that's that. Now, you can either keep it in your calculator, in the memory, or you can write it down. Either way. I'll just go ahead and write it down, but we'll also keep it in our calculator. Okay, you can either write it down or keep that in your calculator. Now, if you don't want to write it down, what you can then do is we need to take it to the 100th power. So we take then 100. That's what we've got there. We use our caret key for the power. And if we didn't write it down and we want to just keep it in our calculator, then you could go get the second. And that A&S is the answer button. And then hit your equals. Okay, and that's going to come out to then be 9. So your final finished answer would be 9. Right? So again, we did our logarithm first, and then we did 100 caret, if you wrote it down, 0.47712, and that comes out to then be 8.999, which is then 9. Okay? And you can either keep it stored in your calculator or you can write it down. Either way, you get the same result. A lot of times I just keep it in my calculator, but sometimes students like to write it down. If you write it down, you'll get the same result. It's just going to be off by a little bit. Did we have any others to look at out of 4-3?
Check out 6 too.
Yep, we can look at 6. Yeah, the other class asked about 6 as well. And 6, we're going to convert it to a logarithm from an exponential. Because right now, it's an exponential. So we have 2 to the negative second equals 1/4. Now, what's our formula look like? Y equals log base A of x converts into x equals AY, right? Okay, so labeling the pieces. Right now it's in this form. So this 1/4, that is your x. The 2, that is your A. The minus 2, that is your y, right? See how I labeled the pieces? And when I convert it, what does it now look like as a logarithm? Okay, we've got our x, which was 1/4, right? So that's going to be inside. We've got our y, which is now a -2. So we have -2 equals log base a, which a is a 2, of, yep, 1/4, right? And that's what we want. So all we did was we just converted it. Is everyone okay with that? Huh? Sure. Yep, we can add 9 to the list also. Okay, so question 9, what we have to do on these is we have to work with a functional value. So we've got f of x equals log base a of x, and we know that f of 4 comes out to be 2. So when I plug my values in, we need to find our a. So that's what we're going to be looking for. We have to find the a so then we can rewrite it. So we know that f of 4 is going to be 2. So the f of 4 would be 2, and that's going to equal then log base a, which is unknown, and what's our value of x? 4. So that's going in here. Now, how can we convert this to make it work? Well, right now it's a logarithm. Okay, so when we look at our formula, remember our conversion formula is right up here. Right now it's a logarithm. So this is my y, this is my a, and that is my x. So when I convert it, what does that convert into and look like then? Well, when I convert it, it looks like it's 4 equals a to the second power. And what do we know? Yep, 2 squared is 4, right? Okay, because 2 squared is 4, right? Now the powers are the same. If the powers are the same, the bases must be the same, so then a must be now what? 2. Now we can rewrite it, and we can finish this out. So now let's go ahead and rewrite this and plug in the new value. So now we want to find f of 16. So our f of x is now log base 2 of x. And we want f of 1 over 16. So let's try to find f of 1 over 16. And this is our y. So I'll just call this our y. Doesn't matter what we use for the variables here, I'll just call this my y. That way it'll convert easily. So we'll just call this our y here. Instead of f of 1/16, we'll say that's y. Now, right now it's an a logarithm. I want to convert this to an exponential. So when I convert it, this is my y, this is the a, and that's the x. And we want x equals ay. So what do we have for our powers? We have a, which is 2. We've got x, which is 1 over 16, and unknown power y. Is everyone okay with that so far? Now, we solved these before. First thing I want to do is I want to get rid of the fraction. So I can rewrite this as 16 to the negative first. So that's my first step. Make it a whole number instead of a fraction. Now, what do we know about the 16? 2 raised to what power gives me 16? Okay, 4, right? Because 2 cubed is 8. Yep, 2 to the 4th power is what? 16. So now I can rewrite this as 2 to the negative 4th power equals 2 to the y, and now the bases are the same, so I know that y must now be what? 4. negative 4 there. Is everyone okay with that? The next section that we're going to look at is 4-4, and then we'll do a little bit of 4-5. So let me go ahead now and pass out the the next homework packet. And this will be due after our fall break. Because next week, remember, is our fall break, and we won't have class at all. This is the new homework packet here. We're going to be looking again at 4-4, and we'll do a little bit of 4-5. These are a little bit tricky. A lot of it is nothing but using the calculator. You have to know how to use the different formulas. So we're going to be doing a lot of calculations here on this. Let's get things sorted out. And we're going to look now at 4-4. And when we talk about 4-4, we're going to be learning about some common bases. Did everybody get a copy?
No.
Oh, yep, I've got one. Oh. Did everybody get one? Oh, you got it? Okay. Oh, no problem. So we're going to talk now about logarithms. And we're going to talk about the common logarithms. And then we're going to learn how to use the change of base theorem. And this is 4.4. Now this is all calculator based. And we're going to talk about the two common bases. The first one is log base 10 of x. All right, log base 10 of x, we can write this as just log x. So if it's a log base 10, then we don't need to write the 10 because we understand that if there's no number, this is log base 10. And that's the calculator key. So we don't need to write the 10 for log base 10. Another one is log base e of x. And log base e of x is ln of x. And this is the natural log. And when we talk about the natural log, that's used a lot in statistics. Whenever you talk about probability and predictions, population growth, bacteria, things like that, those are going to be dealt with on the logarithm scale, natural log. So we use natural log for those. Okay, that's log base e. So that's what that is. It's its own special key in our calculator, the ln key. If it's some other base, then we have to convert it. And now we're going to talk about the change of base theorem. The change of base theorem says this: log base a of x is the same as log of x over log of a. And you can use the natural log instead of the log key. They're the same, as long as whatever you use is consistent. So let's use the change of base theorem to evaluate down some logarithms. So I want you to find this value. And we're going to be using the change of base theorem. So what do we know here? Well, that 5 down below, that is my a. And that 125 is the x. So if I apply my change of base theorem, then that is going to be log of 125 over log of 5, right? and use our calculator. And again, I'll show you both styles so you know how it works on either type of calculator. How would I evaluate this out on this calculator? Well, on this one, we can use our log key. So we hit log of 125. That's the top half, the numerator. Divide that by log of 5. Let me type it in here correctly here. So that's that. Okay, then we're going to divide that by log of 5. And that's going to come out to be then what? 3. You can also use our calculator here. Same thing, a little bit different. 125, hit your log key. Or sorry, 125, hit your log key. You hit the right key here. Right, divide that by then log of 5. And that gives you the same what? 3. Let's do one more. How about I have you find log base 1/5 of 12. Sure, no problem. Right, yeah. Yes, they may come out to be whole numbers, they may not be. Right, and you could have converted this to an exponential, and you would have saw that 5 cubed is 125. Okay, same thing. Now, this is just another way of doing it, so you don't have to use exponentials. It makes it a lot easier. And you could have used the ln here instead of logarithm. You can use any log that you want. It's just that we normally use log base 10 or the ln. But whatever you need to do, you convert it with either natural log or log base 10, and you'll get your answer. Now, how would we convert this one? Okay, this one's going to be done the same way. I like to use log, but you can also use the natural log. And I'm going to go ahead and make this 1/5 a decimal. So as a decimal, it's going to come out to be 0.2. And now I can just work it out with my calculator. This one is not going to come out to be a whole number like the last one, because the last one, 5 cubed, is 125. This one's not going to come out to be a whole number. We're going to have to use our calculator. So we need our 12, and we'll hit our log. Okay, and then we'll divide that by 0.2, log of that. And then we hit our equals, and that comes out to now be minus. And normally we'll round these out to 3 or 4 decimal places, depending upon the direction. But that's going to come out to be a minus 1.54 if we round 4, close enough. So again, how did I do that? I took my 12, hit the log key, divide that by 0.2, hit the log key, and hit the equals key. And that gave me my answer there. On this calculator, how would you do it on this type of calculator? Pretty much the same way. It's just backwards on the order. So you would type log of 12, hit equals, divide that by log of 0.2, hit equals, and that gives you the same answer. So that's how we use our calculator now to evaluate down different bases. If there's no number, it's just log base 10. Next, we're going to look at applications. And one application that we're going to look at is we're going to talk about pH and how pH works. If we talk about pH, and if you take a chemistry class, you're going to do a lot more with pH calculations. But pH is on the logarithm scale, because a small change is a large change. And let me find the pH strip picture so you can see what we've got. And we'll talk about what pH is, and then we'll learn how to calculate. Now, we're not going to go into a lot of detail about what pH is. pH, basically, it's just the number of hydrogen ions. That's for a chemistry class. In the chemistry class, you'll delve a lot deeper into what hydronium ions are and how they work. In This course, all I'm doing is using logarithms to show you how the pH can be calculated. Now, when we look at pH, pH is from 1 to 14. Right in the middle is water. It's neutral. Right? Most water should be around 7. It might be a little lower, a little high, but water's generally around 7. Now, when we start talking about things that are close to 1, like if you look at 1.5, that might be something like sulfuric acid. And sulfuric acid, if we spilled sulfuric acid, it would eat everything. Right? It would eat anything that's organic matter. Sulfuric acid would eat it. Very toxic. Spill it on your hand, it's going to burn your hand. On the opposite extreme, on the base side or the alkaline side, this would be things like, when you get close to 14, this would be things like drain opener, lye. Things that if you spill on your hand, they're going to burn you, right? But they're the opposite of the acid. Now, a small change is a large change. When you go from a 1, well, you can't actually go from 1, but let's say you went from 2 to 3, that's a change of a power of 10 because of the logarithm. Because the logarithm is base 10. So it's 10 times as much. So every small change in the number is actually 10 times as strong. So now we're going to learn how to calculate the pH using this formula and the number of hydronium ions. And again, a lot of this is going to be reserved for a chemistry class. All I'm doing is working through the mathematics. If you take a general chemistry course, they're going to focus a lot on pH, and you'll learn about hydronium ions and what they are. Okay, but in this class, we're just going to be calculating. So here's our formula. Your pH is going to equal minus log of H3O positive ions. That's your formula. Now, there are different ways of calculating this out. You can either use your calculator with scientific notation, or you can split it up using our properties of logarithms. Yep, O positive. That's hydronium ions. And in a chemistry course, they would go into great detail about what those are. In this course, we're just going to talk about them, and they're going to be given to you. But in a chemistry class, you would spend several weeks talking about pH, what pH is. But in this class, all we need to know is 1 is an acid, 14 is a strong alkaline or strong base, and right in the middle is 7 with water. Now let's talk about question 30. We're going to find the pH. And we're going to find the pH of limes. This is page 485. And we're going to try to find the pH of limes. Now, what do we think about limes? Limes are pretty acidic, right? So, the smaller the number, the closer they are to 1, the more acidic it is. So where do you think limes would fall? Would they be above 7 or below 7, do you think? Below 7, right? Because limes are an acid. It's going to be fairly close to 1. Not quite at 1, because again, 1 would be something like sulfuric acid or hydrochloric acid. Things that come in contact with organic matter would eat it or destroy it. Limes are not quite there, but they're still a pretty low pH. So how do we calculate this out? Well, our pH is going to be minus log of 1.6 times 10 to the negative second power. How do we use our calculator for this? You may or may not be familiar with scientific notation in your calculator. Some of you may have seen this before. Some of you may not have. I'm going to show you both calculators, and I'm going to show you how it works. So let's try it in this calculator. Now, I'm just going to keep in mind that I changed the sign. So I don't put the negative in because that's, I think, going to be confusing. So on this style of calculator, to work this out, you just find your LOG key here, and then we want 1.6. How we raise it to the power is we need the double E. And if you look here, right above, in this case, the x inverse, the double E. We want the double E key. Okay, so you have to hit second inverse. That's going to put the E there. Now that E is the power of 10. And what does it raise to? Negative second. And then we hit equals. Now, when we work out pHs, they're going to come out to be positive. We have a negative in front, so we change it. And if I change that and I round to the nearest tenth, that's going to round out to be 1.8. Normally pHs are going to be rounded to the nearest tenth.
Wait, what? You give you negative over there.
Right, but I didn't put the negative in front because that's just another way of confusing people and students. So what I do is I change it at the end. So I just remember that pH is actually positive. Right? I didn't put the negative in front. I could have, but that's one more place you can make a mistake. So I just remember when I get my answer for the pH, you change it, you make it positive.
So
And
if you did put the negative in, it would have became. I mean, if you did,
yeah, I could have done this. But it's just one more place where students can make mistakes. Right, right. And see it would come out positive. Because there's a double negative. It's negative, but there's a negative still here. I don't usually put it in when I work these out. I just remember to change my answer. Because pH is half positive. I think that saves you from making a mistake. Now, does that make sense? Yes. Why? Because we know limes are acidic, and limes are going to be then closer to 1. You can. You can do it that way. I usually don't because it's one more place to make a mistake.
So let's say you don't try to do
You just change it in your mind. You just change it mentally. You can either put the negative in front or you can just remember to change it mentally.
So can you do it again?
Sure.
Without putting the minus and the negative.
Yeah, it'll be the exact same thing. We want to try to find this log, so we hit the LOG key, and then we hit the 1.6. Now we want the double E key, so second double E here, and we want a -2. Now make sure when you plug in that -2, you use this symbol, not this one. Use the negative with the parentheses around it. Hit your 2, and then hit equals. And now I know it's a negative value, but what do I know about pHs? So I just remember mentally to change it. So you can either put the negative in front, which I generally don't do. I just make a mental note that pHs are positive, so change it. And usually you round the pHs to the nearest tenth. And that makes sense because we would expect limes to be on the acid side. What about 32? 32 is lye. Now lye is drain cleaner. And it's 3.2 times 10 to the what? Negative 14th power. Where would you expect drain opener to be? It's going to be base, right? It's going to be in the alkaline side. So that's going to be close to what value? A 7 will be in the middle. Okay, it's going to be close to 14. So 7 is water. I can drink water. It has no harmful effects, right? But when you start talking about like a 13 or a 14 and you drink lye water, that would burn your insides. So this is going to be closer to 14 because it's an alkaline or it's a base. Some people call it a base. Our textbooks call it alkaline. It just means it's not the opposite of acidic. So what would my value come out to be? It should be fairly close to 14 because it's pretty strong. So my pH then would be minus log of 3.2 times 10 to the negative 14th power. So I'm going to show you how to put this one in this type of calculator because, again, everyone has a different style of calculator. Let's look at this one. This one's done a different way. Here's two types. You may have this type of calculator. How would this one work? On this one, we type our number in first. So we type in 3.2. Now, we need, again, the double E. That's going to take care of my power. So we find our double E key. And what power are we raising that to? Negative 14. And then what are we going to do from that? We're going to take the log of that, right? And we're going to change our sign. Now, what did this come out to be? Let's write it down. That's what I got on my calculator screen, right? This is the power here. So, what would this look like in standard notation? If this is times 10 to the first, this would be what? Moved back 1, so it looks like this would be 13 point what? 5, and what do we know about the double negative here? Makes it positive. So that would come out to be 13.5. It just put it in scientific notation. So this represents the number of powers of 10. So I just move it over 1. This style of calculator, let's do this one. You're going to get the same result. Okay, this one's a little bit different because I hit the log key first. Then I need 3.2. We hit second, the inverse key to get the double E. Negative 14. And hit equals. And again, what do? Change it and make it what? Positive. So what is that pH? 13 point what? 5. Okay, so does that make sense how this works? Just using the calculator. I know that we can't really go into the theory behind this because this is something with pH you would cover for about a week in a chemistry class. If you took a chemistry class, they would probably spend a week to a week and a half talking about pH. We're not doing that.
The mile was 3.6 or 3.2?
Which one now?
3.2.
Oh, okay. Which? It's going to be 13.5 when around.
Can you go up?
Sure. Yep, no problem. Okay, so what I did was this is the H3O positive. And that went in my formula here. And depending upon which type of calculator you have, it may spit this out as an answer. Which that's just in scientific notation. And you can just move that one place over and still get that 13.5, right? If you use this style of calculator, you'll get the same result. Because if you just type log of, find the log key, log of 3.2, hit your double E key. We want negative 14 and hit equals. That comes out to be 13.49, right? Which would round to be 13.5. Now, whenever it comes out to be negative for pH, we know pH must be what? Positive. So I always just mentally change it. I think you're better off doing that than plugging in an extra negative and actually making a mistake in the calculator.
So it's always positive?
Yep, pHs are always positive and pHs are always between 1 and 14. That's how they work. 7 is neutral in the middle. Lots of other things are also on the logarithm scale. So pH is one example. We can also talk about earthquakes. And we can also talk about earthquakes and the decibel scale, sounds. So those are two other examples that are on the logarithm scale. So let's look at an example of earthquakes. And here's our formula for earthquakes. And we're going to use this formula in question 66. We're going to look at question 66. So this is our formula. Do what now? Sorry about that. Page 486. Sorry about that. Okay, so page 486. Now, when we talk about earthquakes, they're going to be measured on the Richter scale. What that actually is that's a ratio between the vibrations felt on a normal day from the earth versus the vibrations felt by a seismograph when an earthquake happens. So it's a ratio. Remember, there's always a constant movement of the earth. So it's constantly moving. A seismograph is just going to barely be moving. But when there's an earthquake, remember, seismograph is one of those charts that goes up and down. Whenever there's an earthquake, it's going to go way up and down. Now, how do they determine the magnitude? They use what's called the Richter scale. And it is a ratio of normal day movements of the earth versus that day when there's an earthquake. So we're going to look at question 66. And this is going to talk about the power of an earthquake. On December 26th, 2004, an earthquake struck in the Indian Ocean with a magnitude of 9.1. That is a very, very powerful earthquake. Express this reading in terms of I naught to the nearest 100,000. So what do we know? We know that there was an earthquake in India, in the Indian Ocean, okay, and that earthquake was 9.1, and that's going to equal log of I over I naught. Now, how do we handle this? How do we undo a logarithm? Well, when we talk about logarithms, logs are log base 10. Okay? So we think about them in terms of opposites. So let's take a moment to think about the opposite of a square. What's the opposite of a square? Square root. What's the opposite of a cube? Cube root. Okay? We're talking about log base 10. So the opposite of log base 10 would be the power 10. Okay, so whatever we do to one side, we're going to do to the other. Now, when we work this out, log base 10 and the power 10, well, those cancel. And so now, what do we know about 10 to the 9.1 power? We're going to work this out. It's going to be a huge number. Okay, we want 10 to the 9.1 power. So 10, and then we hit our YX key or a caret key, 9.1, and it gives you this. And this is in scientific notation. And we can either keep it in scientific notation or we can rewrite it in standard notation. That's my logarithm there. Now, we want to solve this for I. So I'm just going to cross multiply. And this gives us I, which is what we want, equals 1.2589 times 10 to the 9th I naught. Or, if we have to rewrite this in standard notation, this is a huge number. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So look at the size of the number. Okay, and that's 0, 0, 0, put the commas in, 0, 0, 9. Okay, and then 2, 5, 8, and then 1. So look at that, and that's I naught there. That should be 9. What does that actually represent? Let's take a second to talk about what that actually is. This is how powerful that earthquake is relating to the shaking of the earth on a normal day. Normally the earth shakes. I mean, we can't feel it, but the earth is constantly shaking, right? It's always moving, and there is some natural vibrations. This is 1,258,900,000 times as powerful as the shaking of that spot on a normal day. So when you talk about a 9.1, that is a very, very, very strong earthquake. And it's almost like 1 billion times as strong as the vibrations felt on a normal day. We can't feel the vibrations, but the earth is constantly vibrating. So there's a number associated with that. And we can compare that to what we felt on the seismograph, and you can see the difference. When we talk about the Richter scale, it's a ratio. So all it is the ratio, the difference between the two. And how do we get rid of a log, base 10? We use a power 10. How would we get rid of a log base 3? Use a power what? 3. How do we get rid of a natural log? We use an exponential. And we're going to talk more about this in the next section. We'll talk about the opposites and how they're opposite of each other. Yeah, either one's fine. This is just in scientific notation. It's a cleaner way of looking at it. But this is what, if I wrote it out, it actually is. It's a really, really powerful. I write it out like this a lot of times because students don't always understand this. This makes more sense. But this is an easier way of writing it. But this is just how much more powerful it is. So when you talk about a 9.1, that is a huge, huge difference between the vibrations on a normal day and the vibrations during that earthquake.
Wait, so a normal day is what?
It's just a value they find. So the earth is constantly vibrating. It doesn't really have a value, but every day it changes. And so there's a seismograph. Maybe that seismograph is way up here in New York. Okay? And it's got a value that day. Whatever it is that day, it feels it in New York. Now, there's an earthquake way over in India. It's not going to really feel that. So they compare the two, and then they find that this seismograph here in the Indian Ocean, it registered this value. The one in New York registered this. They came up and got the ratio, and that's how powerful the earthquake is on the Richter scale. So that's how it's done. But it's done by different seismographs measuring the earth, because every day it's a little bit different. But the earth is constantly circling around the sun, and it's constantly moving. And so it does have a natural vibration. It's just that when the plates get stuck together, it's all at once. So it releases a lot of energy. But that's how they're done. They're done as a ratio. The hearing, the decibels, also done the same way. The decibels are done pretty much the same way on the decibel scale.
Can we do that like more similar to the one in the homework?
Yeah, we're going to look at some of those. That's what we're getting ready to do next. Let's look at question 9. And then we'll do question 10. These are all a little bit different. Okay, but there's several of them that deal with either an earthquake or they deal with the decibel scale. So let's look at question 9. This is out of your homework. And I was planning on doing several of them. They're not really hard. It's just a matter of how do we set them up. So an earthquake had an intensity of 10 to the 6.1 power times more than the reference level of that earthquake. So that's your I naught. What was the magnitude of this earthquake on the Richter scale? Okay, so let's see how we would set this up. What's our Richter scale? We use an R for the Richter scale, so R is going to represent the Richter scale. And that is log, and we don't have to write base 10 because we know it's base 10, of I over I naught. Now, we know that this earthquake is 10 to the 6.1 times as powerful, right? So that is going to be represented by the I. So I is 10 to the 6.1 power I naught. I naught is just the reference. So it's this number, which is huge, times I naught. So it's this much more powerful. So now we can write up our formula, and we're going to see what can cancel here. If I write up my formula, what's going to happen to the I naughts? Yep, one's on top, one's on the bottom, so those can cancel out. Now we've got our R, and that's log of 10 to the 6.1 power. And we can do this two different ways. You can either bring your exponent down, which we've done before. We talked about that a little bit last week. We just bring that 6.1 down, or you can just use your calculator. We'll just use the calculator here. It'll give the same result. Okay, so how do we work this out? We hit our log key. And then what are we looking at? 10 caret 6.1. And then we hit equals. And what does it come out to give you? It comes out to give you 6.1. Now, how many times larger was that? Just so we have a reference. A 6.1 magnitude earthquake is, what, about 1,000,003, something like that, times as powerful as the vibrations felt on a normal day. And that's a 6.1. That's why when you go from a 6.1 to a 6.2, it's a huge change. It's like a factor of 10, just going that decimal point. That's why when they classify them, it's a big deal, whether it was a 4 or a 4.5, because there's a big difference in the power. Even though they're close numbers, it's a big difference. And that's what logarithms are. A huge change is represented by a small change. That was question 9. So is everyone okay with how I did that? Now, when we talk about the decibel scale, well, the decibel scale is going to be done the same way. A different formula, slightly different. We're going to look at the decibel scale. And D equals 10 log of I over I naught. And so question 10 works with the decibel scale. So let's read it, and we'll label our pieces. We'll plug it in, and we'll find our I. The decibel level D of a sound is related to its intensity, I, by this formula. D equals 10 times the log of I over I naught. Now, what is I naught? I naught is going to be the smallest sound you could ever possibly hear. Okay, so it's like a whisper. It's even below. It's really, really small. If I naught, the initial whisper, the smallest sound that you could ever actually hear, is 10 to the negative 12th power, what is the intensity of the noise measured at 93 decibels? Express your answer in scientific notation, rounding to 3 significant digits. Okay, so what do we know? We have our formula here. We know our decibel. What's our decibel of this noise? 93. And that equals 10 log of I, which we don't know, over I naught. And what is I naught defined to be? 10 to the negative 12th power. So that's going to go here. Is everyone all right with that so far? Now, how do we go about solving this? Well, the first thing we need to do is we need to think about this like working with the square root problem. Whenever we work with the square root problem, we need to go ahead and get that square root by itself so we can square. Same concept here. We need to get this logarithm by itself so that we can get rid of it by a power of 10. So we're going to go ahead and divide both of these by 10. And that's going to give you then 9.3 equals log I over 10 to the negative 12th power. We did these a moment ago. How do we get rid of a logarithm? This is log base 10. So to get rid of log base 10, we use power what? Power 10. So that power of 10 and that logarithm, well, they cancel out. Now we have 10 to the 9.3 power equals I over 10 to the negative 12th power, right? We're not going to break it down just yet. What we're going to do is we're going to cross multiply, and then we're going to use our rules of exponents. So we're going to go ahead and cross multiply here. And when we cross multiply, that gives you I equals 10 to the 9.3 power times 10 to the negative 12th power. So all we do is we cross multiply. And hopefully we remember these bases are the what? Same. So that means those exponents can just be added together because they have a common base of 10. And that would give you then I equals 10. We add those together of 9.3 minus 12. That's going to be a minus 2.7. And let's go ahead and get our answer in scientific notation. So that would then be 10. You either hit the caret key or the YX key. 2.7, and make sure you see that it's negative. And that comes out to be this, 0.001. Depending upon how we round, we can round this to 19. Well, let's see, that would be rounding up to be 200 there, right? Because if we round, because that would, if we would take it out that many places, that 5 would make that round up and make those zeros there and round all the way up. And that would be 0.002. And what would this be in scientific notation? Here's my decimal point. So we're going to have to move 1, 2, 3 places. So it looks like 2.00 times 10 to the what power? We went over 1, 2, 3 places. So that's going to be minus third power. Is everyone okay with how I got to that? Or you could just leave it as, I'll take either one. Same thing. They're the same thing. Right? You can either leave it in standard notation or scientific. It says use scientific notation. If you want to use standard notation, that is okay too. Either one is perfectly fine. Okay, so that now should have taken care of a lot of these. Let's do one more. And we're going to look at question 15, because actually question 15 got cut off here. When I ran it through the copier, it cut off that number. It was a larger number. We'll just make question 15. Make sure you see that P is going to be 10. I think it was like 10,000 or something. It got cut off in the copier. So we'll make that P of 10. Now we're going to talk about question 15. And then I'm going to leave the rest of them for you to do. And then we're going to cover just a little bit out of 4.5 because it's a really, really large chapter, large section. And we'll finish it up on Thursday. But let's talk about 15. Quail are game birds that fare poorly when their habitat is encroached upon. Wildlife biologists have discovered that the population P of quail in a region is related to the percent of the region that has been paved with roads and parking lots, according to this formula. Where X is the percent of that region that has been paved. For the particular rural region, P is going to be 10, and I just put the 10 in there. I did the other class the same way, so everybody's got the same numbers. P is 10 because it cut it off, where X is 0. We want to predict the quail population when this region becomes 6% paved. So quail are our little game birds, and what happens is when humans encroach into their population, quail don't do very well. They have to have lots of free range. They have to have a lot of forest and grasslands for them to work on and walk around in. When humans come in contact with them and we start paving and developing land, the number of quail decrease. And they decrease on a logarithm scale. You may not know, but quail are birds native to this part of the country, so they're just small. They're kind of like a Cornish game hen, so they're a small type of hen. So let's work this one out. And the first thing that we have to do is we have to find our K. So we're going to look at this one just like we did last week with the variance, with variation. We've got to find that value of K. So here's our formula. P equals K ln of 30 over x plus 4. And we're going to use, in this case, P equals 10, and x is going to be 0. Now, x is 0 because that is before any houses or any of this land was developed. So this is the number of quail in an undeveloped land. So we're going to plug in our values, and we're going to have to find our K. So our P is 10. Plug that in. Our K, we don't know. That's what we have to find. That is just like our constants from the variation. And then we have ln of 30, and our x is 0. So that's 0 plus 4 there. Okay, so nothing has been paved, nothing has been done. It's completely unimproved land. So that gives you then 10 equals K natural log of, what do we have here? 30 over what? 30 over 4, and 30 over 4 is that 7.5. Now we can finish it. So let's go ahead and find out what the natural log of 7.5 is. We have to find our constant K. And so we'll just take the natural log of that. And that's going to be 2.0149, close enough. K, and that equals 10. And then we can solve this and we can get our constant K. And that gives you a K value now of 4.96 if we round 3, close enough. We could go further out, but 3 places is usually more than enough. And what does our formula now become? P equals 4.963 times 30 over x plus 4. So that's our formula. Sure, Yeah, we just divided both sides by that 2.0149. And that gave me that there. Now, what do we want? We want to take out 6% of their habitat. So if we take out 6% of their habitat, we're going to be using x equals 6 there, because x represents the habitat. And now we rework it, and then find out what the quail population is going to become. And that gives you then 30 over 6 plus 4 is 10. So that gives you, and we need the natural log there. I about forgot. Yep, don't forget the natural log. Natural log goes in front. So what does that give you now? That gives you P equals 4.963 natural log of 30 divided by 10, that makes it a 3. How we should be able to just use our calculator and work it out. So let's go ahead and just do that. We want the log of 3, natural log of 3. And then we'll multiply that by 4.963. And that then gives you an answer of 5. We'll round 45, close enough. And so it went from a population of 10 to 5.45. And the more of their habitat you take away, the faster their population is going to decline. And I know that when I pulled this problem from the textbook, it should have been larger than 10, but we'll just use P equals 10. That way both classes have the same value. Now we do have a little bit of time left, and I want to at least start a couple of questions out of 4.5, because we've got to make sure we can at least get a start today. .5, we're going to be looking at solving logarithm equations. And we need to use some different properties of logarithms. So logarithms have a lot of unique properties. When I multiply in logarithm, I can break it up into addition of 2 logarithms. When I divide in a logarithm, I can break that up into subtraction of logarithms. It is, in this case, if I have 2 things multiplied together, then I can split it out into 2 separate logarithms added together. Logarithms are unique, and they have unique properties, because multiplication in logarithms in 1 log can be turned into addition. Division in 1 logarithm can be turned into subtraction. Powers can be broken down. When you have a power in a logarithm, and I know we've used this one before, this power can be brought down. So r of log of x. Okay, so you can bring powers down. Now, when we have a log of 1, irregardless of the base, is always going to be 0. Okay, so log of 1 is always 0. So that's something that we need to remember. We use it once in a while. But log of 1 is 0. Also, if the logs are the same base and number inside, then it comes out to be 1. So these are properties that sometimes we have to use. And the equations in 4.5 require a little bit of thinking. They're kind of like what we did back in chapter 1 when we looked at things in 1.6, 1.6 and 1.7, where we had to really think about how to work with different types of equations. Same thing here. We've got to use some properties of logarithms to be able to work them out. And we're going to start with at least one question, maybe 2 if we have time, of something out of the first 3. So I'm going to pick one of these from our textbook to look at. 63 is what we're going to look at. We'll do 63, and then if we have time, we'll do some like 4 and 3, or 4 and 5. So we're going to look at this one from our textbook, and this is on page 497. And we're going to look at question 63. Uh-huh. Yeah, sure, no problem. Not a problem at all. Yep, sure.
Professor, that log is log 1 equals 0.
Log of any base. Log A, it doesn't even matter what the base is. Log of any base of 1 is 0. That's just a constant. Anytime you have a log of 1, it is 0. And when these are the same, it's 1. And we don't use these properties a lot, but we sometimes do use them. And they're actually in the textbook as well. And let me give you that page number for these. So these are actually going to be in your textbook on page 469. If you want to reference that. But they're in your textbook. Now, we're going to be using these properties to get it down to something that we can deal with. And 4 or 5 is a very difficult section. It's not an easy one at all because there's all different types of questions. And we're going to look at 63. And we're going to learn how to handle this one. Now, what we have to do is we have to get this to where each side is a natural log so that we can eliminate the natural log. When we looked at our properties back here, two things that are multiplied together could be split up, right? So the converse is true. So this is addition. So I can rewrite this as this. Because sometimes you may need to go from one way to the other. So you may have to manipulate them around. Now, why did I do that? I did that so I can get rid of the natural log. Now, what is the opposite of a natural log? Well, when we had log base 10, we used a power of 10. When we talk about natural logs, that is log base e. So to get rid of a natural log in ln, we use e. So we take both sides to the e power. Now, that means that those cancel and those cancel, and look at what we're left with now. We are now left with 7 minus x times 1 minus x, and that equals 25 minus x. And we've solved these before. Now, they're not much fun to solve, but what would we do? Eventually, we've got to FOIL this out, okay, and we have to set it equal to what? 0 and factor. So it's a couple more steps, but let's go ahead and FOIL this out. So I'm going to FOIL it out first. So 7 times 1, that's a 7. 7 times a negative x, that's a minus 7x. Then we've got a negative x times 1, that's a minus x there. Minus x times minus x, that makes it a positive x squared. Those can go together, and I'm going to write it in the correct order. So now we've got x squared. I'll write that first. We've got a minus 8x plus 7 equals 25 minus x. Is everyone okay with that so far? Now, what do we need to do? Okay, yep, set this equal to 0. So subtract off your 25 and add on your x. And now we have something that should factor out nicely. Was it minus 14 there, I believe? Because 7 minus 25, well, that's no, minus 18. Minus 18. Now let's make sure. Did I add right here? 25, 7 minus 25, and that should give you the 18. Did I make a mistake? Let's make sure, because something doesn't look right. Okay, let's make sure that, oh, yep, I made a mistake right there. That's why it didn't come out right. Should be a 7 there, shouldn't it? My mistake. I just wasn't careful, because minus 8x plus x makes it a minus 7x, right? Now it'll factor. I knew I made a mistake somewhere. So it should be a minus 7. First times the last, there's no number, so put our 1 there. 1 times a negative 18 is a negative 18. And what two numbers are going to work to make this factor? Okay, negative 9 and positive 2. Factor that down into x minus 9. X plus 2 equals 0. So x equals 9, and x equals now what? Negative 2. Are you all finished? All right. And do you have your take-home file?
Yeah.
Yeah, okay. Yeah. If you can bring that back to me, that'd be great. That way I can get it all ready for you. Okay, so now, before we are finished, though, we have to double check them. Because remember, we did questions in 1-7 where you couldn't have things like division by 0 or negatives underneath the root, right? Well, you can't take the negative logarithm of a negative number. So if I plug either of these in and it comes out to be a negative inside that logarithm, I can't do it. So only one of these is going to work. Now let's go back and look at our original. Our original equation is the natural log of 7 minus x. All right. Thank you very much. Yep, I'll get that graded for you. I'll probably have it graded the next couple of days. You can check in Canvas. Okay? Yep, you're welcome. Okay, so one of these is not going to work. And let's go back and look at our original. And this will be the last one that we're going to work through, because I don't think we have time for another one. And let me find the sign-in sheet, too, before I forget. It should be around here. Here's the sign-in sheet. And I'll put the homework out. Here's the sign-in sheet. Now, one of these is not going to work. Okay, let's look and see. And all you have to do is visually look at it. Why is 9 not going to work? Because 7 minus 9 would make it what? Negative 2. And can you take a logarithm of a negative number? So if any of those logarithms come out to be negative, you can't do it, so it doesn't work. Now, what about negative 2? Why is it going to work? Well, 7 minus a minus 2, that makes it 7 plus 2, which is 9. You can take the natural log of 9. 1 minus a minus 2. Well, that's a double negative again, and that makes it positive, right? 1 plus 2 is 3. You can take the natural log of 3. What about negative 2? Here, double negative makes it a positive. 25 and 2 makes it 27. So that you can do. So 9 does not work. So here's our homework for next class period. What we have done so far is you should be able to do 4, you should be able to work through all of them. 4.5, you should be able to do, or at least try, 1 through 3. If you have questions about those, we can go over them next class period.
So just check if they work and like if you get them if you don't check how it goes.
Right, don't have to do the whole thing. No. Because it's like when you check for division by 0. If you can see that it gives you division by 0, throw that solution out. This one we know 9 doesn't work because that gives me a negative, so automatically out the door.